So we're going to discuss the last portion of the calculation of doses, which is particularly on calculation of dose based on body surface area. So the body surface area method of calculating drug doses is widely used for three types of patient groups, namely cancer patients receiving chemotherapy, geriatrics, and pediatrics patients. Body surface area is recommended as the principal basis for drug dosage as the rate of metabolism or redistribution of a drug is proportional to metabolic rate. So which in turn reflects heat losses, which as for any warm object are generally proportional to surface area. So many measurements of organ size, fluid compartment volumes, and assays of blood concentrations of drugs correlate well with body surface area or the BSA. Average adult is considered to have a BSA of 1.73 meters squared. So if you're going to compare age, weight, and BSA, the more accurate calculation of those would be based on the body surface area. So classification methods of those calculation based on body surface area. So we also have three: ratio and proportion, dimensional analysis, and the reference formula. For the reference formula, we have to identify first the BSA of the patient before we identify the specific dose for a specific patient. So for the BSA, we're going to use this formula. So the unit for BSA is in meters squared. Since you are measuring two dimensions, so it is the square root of the height in centimeters times the weight in kilograms over 3,600. And then for the computation of the dose using the BSA, so we have two formulas. Patient's dose equals patient's BSA over 1.73 meters squared times the drug dose in milligram. Child's dose also is equivalent to BSA of the child times the dose per meter squared. So let's discuss some examples of calculation of the BS calculation of the BS calculation of those based on BSA, body surface area. So if the adult dose of a drug is 100 milligram, calculate the approximate dose for a child with a body surface area of 0.83 meters squared. So what is now the adjusted dose of a particular child if he or she has a body surface area of 0.83 meters squared and the adult dose is 100 milligrams. So is it higher than 100 milligram or lower than 100 milligrams? So again, we have to write the given and identify the unknown. So the given here is the BSA of the patient, which is equivalent to 0.83 meters squared, and the adult dose is 100 milligram. And then the unknown is the adjusted dose for this particular child. So for the solution, the first solution is the reference formula, wherein we're going to use patient's dose equals patient's BSA in meters squared over 1.73 meters squared times drug dose in milligram. So substitute our given to our formula. So 0.83 is the BSA, and then the adult dose is 100 milligrams. So 0.83 meters squared times 100 milligram over 1.73 meters squared. The adjusted dose now for this particular patient is 47.98, or if we will round it off to the nearest whole number, that's equivalent to 48 milligrams. So cancel the unit of meter squared. What's left? It's just the milligram. For ratio proportion, again, it is between two ratios or two pairs. So it will look like this, the solution. So 100 milligram is the dose for an average patient which has a body surface of 1.73 meters squared. What about now if the body surface area is only 0.83 meters squared? What is the equivalent amount or dose of the drug? So cross multiply each side, that will become 0.83 meters squared times 100 milligram in x milligrams, so since this is the missing, multiplied by the usual body surface area, which is equivalent to 1.73 meters squared. And then your solution will become like this. X milligram equals 100 milligrams times 0.83 meters squared over 1.73 meters squared. Cancel the unit of meter squared. What's left? It's just a milligram. So the answer is still the same. 47.98 or 48 milligrams. For the dimensional analysis, again, you have to consider which part of the problem doesn't have a pair. So in this particular one, it's the body surface area of the child. So you will multiply the body surface area with a ratio that is equivalent to 100 milligram over 1.73. So you will still get the same answer, which is equivalent to 47.98 or 48 milligrams. Next problem. So what is the dose of a drug at a dose level of 300 milligram per meter squared for a child determined to have a body surface area of 1.25 milligrams squared? So would it be higher or lower than 300 milligram? So let's write now the given and identify the unknown. So for this particular one, the given is the dose per meter squared is equivalent to 300 milligram per meter squared, and the child's BSA is 1.25 meter squared, and the unknown is the adjusted dose of the child or for this particular patient or child. For the solution, we will use this formula. So child's dose equals BSA of the child in meter squared times the dose per meter squared. So that's the importance of knowing the given and knowing also the unknown so that you will determine which is the most appropriate formula that you're going to use. So child's dose, substitute now you're given to this particular formula wherein the BSA is equivalent to 300 milligram per meter squared. So multiply, you will cancel out the meter squared since one of them is found at the numerator and the other one is found at the denominator. And we will retain the unit of milligram. The answer now is 375 milligram is the adjusted dose based on the body surface of this particular child. Next problem. So if the adult dose of a drug is 75 milligram, what would be the dose for a child weighing 40 pounds and measuring 32 inches in height? So since the body surface area is not given or was not given, we have to identify the body surface area of this particular patient. For the given, so the weight of the patient is in pounds, the height is in inches, and the adult dose is 75 milligram. For the first solution, we have to compute for the body surface of the child using this particular formula. But in this formula, the height should be in centimeter and the weight should be in kilogram. So this means that we have to convert the weight from pounds to kilograms, which is now equivalent to 18.18 kilogram. So how do we get the 18.18 kilograms? Multiply 40 pounds multiplied by a ratio that is equivalent to 1 kilogram per 2.2 pounds. Cancel the unit of pounds. What's left? It's just the kilograms. So this is now equivalent to 18.18 kilogram. Next would be the height of the patient. So since this is inches, we have to convert now the unit from inches to centimeters. So by multiplying 32 inches with a ratio that is equivalent to 2.54 centimeter over 1 inches, answer now is 81.28 centimeter. And substitute now are given. So the height and the weight in kilograms and centimeter for the height divided by 3,600, and then get now the square root of the answer. Your answer now is 0.64 meters squared. Alright? So before you get the square root, you get first the product and the quotient. So before you get the square root. So answer for this BSA of the patient is 0.64 meters squared. So the meter squared is not actually present, but we will assume that the unit now is meter squared. Then we can now already compute for the dose of the patient using this particular formula. Patient's dose equals patient's BSA in meter squared over 1.73 meter squared times the drug dose in milligram. And then substitute now our given. So the BSA in the drug dose or the adult dose, which is equivalent to 75 milligram. It will look like this. So 0.64 meters squared over 1.73 meters squared times 75 milligram. So you will cancel the unit of meter squared. What's left? It's just a milligram. So the answer now for this particular patient is 27.28 milligram. So for a patient that has a weight of 40 pounds and 32 inches of height, the adjusted dose is 27.28 milligrams. So that is now for the calculation of doses.